The Junkers Jumo 205 was built to fly low and far. 12 pistons, 6 cylinders, no cylinder heads, a two-stroke opposed piston diesel running on the same fuel as the ships it crossed below, and at low altitude over open water, nothing in 1930s, aviation matched its range per unit of fuel. Then the war arrived. The war needed altitude. The same thermodynamics that made the Jumo 205 exceptional at sea level made it inadequate above a certain ceiling. The engine didn't fail. The conditions it was built for were suspended at the moment it had proved what it could do. By the end of this, you'll know exactly why the most efficient aircraft engine of its era was retired at the peak of its operational capability, and why efficiency had nothing to do with the decision. And most people assume an engine disappears because something better replaced it. The Jumo 205 wasn't replaced in the domain it was built for. It was retired because that domain was suspended. By the end of this, you'll understand the specific conditions that made this engine unbeatable and what happened when those conditions stopped being the conditions anyone needed. Junkers Luftfahrzeugwerk in the late 1920s was not a company in difficulty. It was a company with precision engineering capability, a civilian market to build, and a specific problem to solve. Long-range overwater aviation was expensive in ways that mattered commercially. The fuel required to make a transatlantic flight possible was a large fraction of total operating cost, and conventional spark ignition aviation engines of the period ran on high-octane petrol, refined. A volatile, costly, and absent from the marine supply chains that served the ports and harbors any long-range flying boat route would actually use. Diesel fuel was different. It carried more energy per liter than petrol. It was far less volatile, a relevant consideration when storing large quantities in an aircraft over open water for 14 hours. And it was available at marine fuel depots across the Atlantic Basin because cargo ships had been running on it for decades. An aviation diesel, if it could be made to work at acceptable weight, solved 3 problems simultaneously: fuel cost, fuel risk, and fuel availability at the endpoints of any serious long-range route. The Jumo 205 was Junkers' solution. The architecture was opposed piston, 2 pistons per cylinder approaching each other from opposite ends, no cylinder head, and combustion forming in the space between them at closest approach. 6 cylinders, 12 pistons, 2 crankshafts, 1 at each end of the cylinder bank, geared together at the front. 2-stroke cycle. Every revolution produced a power event in every cylinder. The thermal efficiency that resulted from eliminating the cylinder head, no heat loss through a passive lid, both pistons doing useful mechanical work, was the source of the fuel economy. At low altitude, in the dense air where the 2-stroke scavenging process worked without the complications that altitude introduced, the Jumo 205 produced range figures that contemporary petrol engines could not approach. The operating envelope was not a limitation discovered after the fact. It was the design intent. Junkers was building an engine for a specific kind of flying: low altitude, a long distance, endurance over water. The routes that required those characteristics, the transatlantic mail services, the long over-ocean connections that European airlines were beginning to develop in the mid-1930s, were exactly the market the Jumo 205 was built to serve. By 1937, the evidence was operational. In 1937, Lufthansa put the Jumo 205 into commercial service on the North Atlantic. The aircraft was the Bloem & Voss Ha-139, a 4-engine flying boat operating the Lisbon to New York mail route. The crossing took roughly 14 hours at low altitude above the water, 4 Jumo 205 engines running at sustained cruise power, the fuel load calculated against a range margin that contemporary petrol engines of comparable power could not have matched. These were not demonstration flights. Lufthansa ran scheduled operations across both the North and South Atlantic by 1939. The Ha-139 lifted from the Tagus in the early morning, engines settling into their cruise node above the Atlantic, the cargo hold carrying mail bound for New York, the whole operation running on the same fuel as the ships crossing below. The engine was doing exactly what it was designed to do. The question was whether the world would keep needing that specific thing done. The Ha-139 operations across the North and South Atlantic between 1937 and 1939 were not a trial. They were a commercial service, and they worked. Lufthansa flew the routes on schedule. The Jumo 205 logged operational hours over open water and conditions, salt air, sustained low-altitude cruise, the long uninterrupted power demands that would have exposed any fundamental reliability problem quickly. No fundamental reliability problem appeared. The fuel economics that had justified the engine's development held in service. An aircraft leaving Lisbon carrying mail for New York, burning diesel at a rate that made the route commercially viable, was the confirmation that Junkers had been building toward since the late 1920s. The engine was proven. The market it was built to serve was growing. Then, the altitude ceiling made itself visible as something other than a design parameter. At low altitude, the two-stroke scavenging process that gave the Jumo 205 its thermal advantage worked with the density of sea-level air. The sequence was tight but manageable. Exhaust ports uncover, burned gases escape, intake ports uncover. Under the supercharger pushes fresh charge through from intake to exhaust. Both pistons reverse and compress. The window in which both sets of ports are open simultaneously, the scavenging window, had to be long enough to sweep the cylinder clean and short enough not to lose fresh charge through the exhaust before it closed. At sea level, the air density supported that balance. The supercharger pressure required to maintain it was achievable without compromising the thermal efficiency the whole design depended on. Altitude changed that balance structurally. As ambient air pressure dropped, maintaining adequate scavenging pressure required more supercharger work. More supercharger work consumed more of the engine's output and introduced heat that the two-stroke cycle had no equivalent of the four-stroke's dedicated exhaust stroke to manage. And the efficiency advantage that made the Jumo 205 exceptional at low altitude did not scale upward. It degraded. At the altitudes, a military combat aircraft needed to operate above 4,000 meters, above 6,000 meters. The engine that had crossed the North Atlantic on a fuel load, calculated to the liter, became an engine producing diesel-level weight and complexity without diesel-level economy. The specific window in which it was unbeatable had a ceiling, and that ceiling was fixed in the thermodynamics, not in the engineering tolerance. The Luftwaffe's requirements were not set against the Jumo 205 specifically. They were set against what the air war required. Bombers needed altitude to survive interception. Reconnaissance aircraft needed altitude to stay above defensive fire. And the entire operational logic of strategic aviation in the late 1930s was moving upward, and it was going to keep moving regardless of what any single engine program could offer at the other end of the altitude scale. Junkers could see where the requirements were heading. The Jumo 205 had no path into those requirements. That was not a failure of ambition or development. It was a fact about the thermodynamics. When the war suspended Lufthansa's transatlantic operations in 1939, the Jumo 205's primary application stopped with them. The civilian long-range routes that had justified the engine validated it in service and were beginning to demonstrate its commercial case ceased to exist as an operational reality. The military missions that replaced them needed the one thing the engine's architecture could not deliver. The Jumo 205 wasn't retired because it failed. It was retired because the conditions under which it was unbeatable were suspended at the exact moment it had finished proving what it could do. The engine didn't run out of capability. It ran out of the conditions under which its capability was relevant. After the war, the civilian long-range aviation market, the Jumo 205 had been built to serve, resumed. The transatlantic routes reopened. The flying boats that had carried mail across the Atlantic before 1939 were gone, replaced by newer aircraft designed around a decade of wartime development that had pointed the industry toward altitude and speed rather than endurance and range economy. The Jumo 205 did not come back with the routes it had pioneered. The reasons had nothing to do with the engine's capability in the domain it was built for. and they had to do with what the industry had learned to want in the decade the engine had spent on the wrong side of the war's requirements. The engineering teams that had developed and refined the Jumo 205 through the late 1930s were dispersed by 1945. Some were absorbed into other Junkers programs during the war. Some were lost in the general collapse of German industrial organization. The documentation survived in fragments across archives that post-war Allied technical collection divided between competing programs. What the documentation could not carry was the accumulated understanding that built up in people over years of operational service. The specific feel for scavenging parameters under varying load conditions, the small adjustments to phasing timing that distinguished an engine running correctly from one running adequately. And that kind of knowledge does not survive dispersal. It exists in the hands and ears of the people who built it, and by 1945, those people had scattered. The jet engine's arrival eventually foreclosed what remained of the window. By the early 1950s, jet-powered transatlantic service was becoming commercially viable. The fuel economy argument that had made the Ha-139 routes attractive, the argument the Jumo 205 had been built to support, ran directly against the operational momentum of an industry that had spent a decade learning to build and operate something entirely different. There was no institutional weight behind a return to diesel long-range aviation. The Jumo 205's thermodynamics had not expired. The conditions required to bring them back into application had. The principles did not disappear entirely. In the 2000s, an American company called Acades Power developed opposed-piston two-stroke diesel engines for military vehicle applications, drawing explicitly on the same thermodynamic logic Junkers had identified in the 1920s. The thermal efficiency that comes from eliminating the cylinder head, both pistons performing useful mechanical work, the power density achievable from a two-stroke cycle running in dense air at ground level. The engineering tools available to Acades, computational fluid dynamics, modern materials, manufacturing tolerances Junkers could not reliably hold, transformed what the architecture could deliver. The thermodynamics Junkers had identified were confirmed with tools that did not exist when the Jumo 205 first ran. The conditions that had made it the answer to a particular question had not returned. The answer itself had been correct all along. The Jumo 205 wasn't retired because something exceeded it. It was retired because the specific window in which it was unbeatable closed at the moment it had finished proving what it could do, and by the time that window reopened, the world had decided to use a different kind of engine. What the Jumo 205 story demonstrates is something harder than failure or success. The engine solved the problem it was built to solve, completely and in operational service. The conditions that made that solution matter were suspended by events that had nothing to do with the engine's merits. The institutional knowledge required to sustain it dispersed before those conditions returned. The gap between a correct engineering answer and the survival of the institution that produced it is where the Jumo 205 went. Not into failure, into timing. If this is the kind of engineering story you want more of, subscribe. There are more of them.